Alright, welcome to the lecture on DC circuit. Okay, so there will be in total two videos. Okay, this is part one, right? Now, mainly, what is the main idea of this chapter? Okay, is to find out how your current, okay, how your potential difference, and how the resistance, okay, will behave in either a series or a parallel circuit. Okay, and then of course making some calculation based on it. Okay, first thing first, right? Let's look at what series circuit. Okay, how are current, potential difference, and resistance, how are they related? Okay, this is a summary of all the symbols for all the electrical devices that we have. Okay, now what are the more important ones? Okay, first of all, the switch. Second, the cell, right? If we have more than one cell connected together, that's called a battery. Okay, one of them is called a cell. Okay, followed by the light bulb. Okay, and there's this thing that's called a potentiometer. Basically, it's a device that controls uh, how much potential you want a device to have. Okay, then we have a light dependent resistor, and then afterwards a fixed resistor and a rheostat. Okay, a resistor that changes its resistance. So basically, it's the same symbol as a resistor but with a diagonal arrow head. Okay, a fuse is just a box drawn through a wire. An ammeter, a voltmeter, okay, and also this thing that's called earth connector. So these three lines, right, represents the earth, or basically the action of providing a path with least resistance for the current to flow. Okay, so these few are the ones that you must uh, remember. Okay, now in summary, there are a total of three different kinds of circuits. Okay, one is of course a closed circuit, right, whereby it's a closed loop path connecting the components together. Second of all is an open circuit, right, whereby there is a gap. Now a gap will represent that there's a large, or infinite resistance, right? The current, or rather the electrons, are not able to pass through this gap, okay, because there's no conducting path for them to move through, right? Then followed by the third one, which is called a short circuit. So what does a short circuit do? Basically, it provides a path of least resistance. So current electrons, they are very smart. They will always choose the path with the least amount of resistance to flow through, right? And then they will not need to they will bypass uh, the more difficult path, right? This path that is higher resistance. Okay, now take note, this short circuit only takes place for, let's say, if the path is no resistance at all, right? Then they will take this path. But if let's say there is a component over here that has less resistance, they will still move through each of the path. Okay, they'll move through the two paths together. You'll see that in the parallel circuit. Now, let's take a look at a series circuit. Okay, let's use the PHET. Right, so over here, this is an example of a parallel circuit. Right, so I'll just use this light bulb as a pointer. Okay, so if you see, this is a cell, right, connected through the various wire. This is a switch. Then afterwards, moving through two resistor. Now what you're seeing now is actually the electron flow. So which means if I close the switch, you will see how the electrons are flowing, right, from the negative terminal out. right? All the way from negative terminal out, move through, and back to the positive. That is the electron flow, right? But if I switch it to the conventional current flow, it's from the positive terminal. Alright, now let's try and measure how would the current, okay, for the series circuit, how will it behave? Okay, so this pointer will allow me to examine what is the current at that point. So it's 0.45 ampere, right? I'll move through this and you observe how does it change. Okay, even moving through the resistor, right? You will see that actually the current remains the same at every point, right? That's one unique characteristic of a series circuit because there's only one path for the current to move. So inevitably, of course, at every point it has to be the same amount of current. Right? So that's for the current. Now let's look at how the potential difference will behave at every point of the current. So if let's say again it measures the potential difference, right? Right. So if throughout the wire, right, within the same length of the wire, it will be at the same potential, so there won't be any difference. Okay, okay, until I pass through a certain point. So you'll see that it's always zero until I pass through a certain point. Right? You observe that once I pass through this uh, resistor, it gives me the potential difference at these two particular point. So in this case, it's 4.5 volt for one of the resistor. Now what happens if I jump on to the next resistor? Okay, you will see that the potential difference will also be 4.50 volt. Now that is because these two resistors have the same resistance. Okay, this means that the potential difference across one of the component will be 4.5 volts. And coupled with the current running through it, 0.45 ampere. Right from this, you will be able to calculate what is the resistance of one of the resistor. Or rather, you can calculate what is the resistance of this resistor from R equals to V over I. Okay, now what do you think is going to happen if let's say I measure the potential difference at the 2 points here and here, right? In between the two resistors, what do you think will happen? Okay, let's find out. You realize that it actually adds up the potential difference. And these two potential difference, right, the sum of it, right, actually gives you back the same value as the EMF of the source. Okay, so what this means is that the potential difference across one of the resistor, okay, or rather the sum of the potential difference give you back the EMF. Okay, so if we go back to our summary here, what's the three main ideas for a series circuit? So the current is going to flow through as one path. So the current at the first point here versus the current at the second point here, they will all be the same. Okay, so the current at the first point equals to the current at the second point, right, equals to the current at any point. Second of all, how will the potential difference change? Okay, based on what we saw just now, the potential difference across one of the component and the potential difference across the second component, right? The sum of this potential difference will give me the potential difference of the EMF. Okay, so let's say for example the EMF denoted with a V and a subscript E equals to V1 plus V2. Now because of this, right, you will be able to calculate what is the effective resistance of these two. Okay, this is like the resultant resistance. So it's the same as if I have one entire block of resistor R3, right? Or rather the total resistance. Total resistance. Oh, okay. Sorry, in this case, since they use RE for effective resistance, let's change it to RE. So RE will just be equals to the resistance contribution, right? The sum of the resistance. So RE equals to R1 plus R2. So that's for a series circuit. Now, let's look at one example. In figure 14.9, two resistors with two values of 2 ohms and 1 ohms are connected in series to a 1.5 volt of a battery. So VE, or you can use EMF, same thing. Okay, R1, R2. Right, what would be the effective resistance? So the effective resistance for the first one, RE, will be equals to, since they are in a series circuit, so it will just be the sum of the resistance. So RE equals to R1 plus R2. Okay, that gives you 3 ohms. And this symbol is called ohms, remember. 1B, what would be the potential difference across each of the components? Okay, so because they have different resistance, so will the potential difference be different for each of them. So for 1 ohm resistor, okay, V equals to IR. Depending on what formula you want to use that, right? You can use R equals to V over I also. Doesn't matter. The same thing. So if let's say I want to use this one, V equals to IR. So V1 equals to the current running through the first one times the resistance of the first resistor. Okay, sorry. Oh, first ohm resistor is R2, sorry. Right, because based on what I've defined just now. So this will be equals to, since the current is the same at every point, right? We can calculate what is the current across the entire component. Okay, so a side thing, the resistance of, sorry, the current of the total from the circuit is equals to the EMF divided by, sorry, VE equals to IT times RE. So IT equals to VE divided by RE. So VE is 1.5, right? That is the EMF. So 1.5 divided by RE, which is 3 ohms. Right, this will give you 0.5 ampere. So therefore, since the current at every point is the same at 0.5, right, which means that my I2 will also be 0.5 times R2. R2 in this case, because for the first 1 ohm one, it will be 1, 0.5 times 1. So 0.5 volt. Okay, then for the 2 ohm resistor, again, V1 because based on what I define here, my R1 is 2 ohms, R2 is 1 ohm. Okay, so V1 equals to, okay, and multiply by I1, which is 0.5 ampere, because the current at every point is the same for series circuit, times R1, which is 2 ohm, okay, equals to 1 volt. Okay, so there you have it, the potential difference across each resistor. Now, another way you could solve this, right, is by just taking VE equals to V1 plus V2, right? So to find V1, just take the EMF minus the the potential difference you found in the previous part. So 1.5 minus 0.5, that gives you the same answer, 1.0 volt as well. Okay, second one, the 2 ohm resistor in figure 14.9 is replaced by an unknown resistor with value R ohm. So this has been replaced with R ohm. And the current flowing is found to be 0.1 ampere. What is the value of R? So now since that the new I T, the total current is 0.1 ampere, okay, VE equals to IT times RE. So I want to find what is the new effective resistance. So VE is 1.5 as we found just now, right, equals to IT, which is 0.1, the new value of the total current, times RE. So RE equals to 1.5 divided by 0.1, that gives me 15 ohm. Okay, so since RE equals to the new R plus 1, right, 15 equals to R plus 1, the R will just be equals to 14 ohm. Okay, that's clear. So this will be a typical solution that you can have. Right, at any point if you find that I'm moving on too fast, please either slow down the video or pause it, okay, to look at what you need to copy. Okay, so that's for series circuit. End of part 1.